Hello, everyone, and welcome to another session of Pre-Calculus Review. We're probably nearing some of our last sessions now, and I'm pretty sure this is the only topic that I really have left to teach. So, here is the concept of a matrix. So, you might have seen something that looks like a series of numbers within a bracket. What does this mean? Well, this is what's called a matrix. A matrix is a way of showing a set of numbers. So, uh, today we're gonna talk about just what this looks like and how it's operated before we move on to the usages. Usages we will probably cover in the next session. So, if you look at here, uh, what do you see? Inside the bracket, you see four numbers, right? Do you think there's any difference between this and this? Or even two? Do you think there's any difference between these? Well, to be more exact, if there is a difference, what do you think makes the differences significant? So, comparing this one to this, the main difference is that the places of the numbers are switched, right? So, what makes it matrix unique is that in a even though it's just a set of numbers, like a list of numbers, position of where each number is placed is unique. And likewise, the setup of the matrix itself. So here we have two columns, and two columns and two rows, right? Well, here we have, well, four columns and one row. This type of setup makes a clear difference in the creation of a matrix as well. Even though it's a total of the same four numbers, these numbers eventually make a difference. Let's look at what parts of a matrix are referred to as. So inside of this matrix, we have, again, two columns, two columns, and two rows, right? So the first row is referred to as R1, and the second row is referred to as R2. Now, when stuff like this is used, it's because sometimes the question asks you to change the internal numbers of the matrix by using these types of notations. For example, if they say R1 plus 3, what you do here is that to row 1, you add 3 to each number. Because row 1 refers to 5 and 7 both, you need to add 3 to both. So it's like 5 plus 7, 5 plus 3, then 7 plus 3. So effectively, this would become 8, 10 to 3. And remember that whatever is put first in the operation is the row that you are performing the operation itself on. For example, if you were to write add row 1 to row 2, so what this does here, of course, you see here that the row itself, we're now referring to row 1 and row 2, right? Row 1 was that. Oh, and let's change this back. We're not talking about this one here. We're just talking about 5, 7, 2, 3. Starting all over. We didn't need to erase that. Starting all over from the base here. So What this does is that this says we want to replace the second row, this here, with the addition of R1 plus R2. So this makes this 5, 7, 7, 10 on the bottom. Not 8, 10, because we added 2 and then 3. If this were 3, we might have gotten 8 and 10, just like the other answer again. But it's different because we're putting it on the second row instead of the first. Now, oh, that doesn't work. Sorry. What about adding different matrices to each other? So, say we add 2, 4, 6, 8 plus, 0, 0, 3, 1. What would this equal? Well, the way you do these is super simple. You simply just add uh, the two corresponding numbers and make the same dimensional matrix. So spell that out. It would be 2, 4, 9, 9. You see how 9 is 6 plus 3 and this 9 is 8 plus 1? You just add them to the course by their corresponding positions. You add 2 to here. You add 4 to 0. You add 6 to 3. And you add 8 to 1. You get us this. It's the same for subtraction as well. 3, 5, 1, 2 minus 6, 8, 0, 3. You subtract the corresponding numbers, but well, this time order matters. So you're subtracting 3 by 6, which makes negative 3. And don't worry, there's no rule against numbers in here not being able to be negative numbers, so don't worry about anything like that. Becomes negative 3. This becomes 1, and this becomes negative 1. Now, the problems that you'll see that utilize this might be just simple operations like that, but you might also see things that involve variables of some kind. So we could have something like 3, 5, 8 plus 4, 9, 2, 1 equals 12, 12, 7, 9. Uh, Mind you, this is not 72, this is 12. If you had this, what would you think? What would x equal have to be in order to do this? Well, if you think about it, everything here is irrelevant, right? Everything here is relevant, and everything here is rel- relevant, irrelevant. You're only looking at the position of the variable, which is x, and you can turn this into x plus 4 equals 12, and with simple algebra, we get x equals 8. This can they can change this up by going something like x 2 4 y plus 2 z 3 0, and have this equal something like 8 uh 7 negative 2 9. Think about this. You can divide each one of these up, even if there are, because each position is treated individually. You can kind of solve each of them individually without having to account for the other things. So this is 8 plus 2 equals 8. This is 2 plus z. Oh, yeah, this is a z, by the way. z equals -2, y plus 3 equals 9. Solving these one by one, x equals 6, z equals -4, and y equals 6. So that's essentially it for addition and subtraction of matrices. Next, we're going to show you how to input, let's, because matrices, these types of calculations, when the matrix gets bigger, like we're only looking at a 2 by 2 matrix here, right? 2 by a 2 by 2 matrix. What if it becomes something like 5, say 5 columns and 5 rows? What are you going to do then? When you have to do the operations, it might become way too tedious to actually do them out by hand, especially if you need to show the work. So if you look on your calculator, there's, after pressing second, if you press x to the -1, assuming you're using a TI-84, or just find the option that says the word matrix on it, will bring you to a 3 on a on most Texas Instrument calculators, will bring you to a 3-part menu that says name, mass, and edit. In names, it gives out the list of each type of matrix. They're defined by alphabetical. They're defined by alphabets, as in A is one matrix, B is one matrix, C is one matrix, all the way on until you get to J. Mass lets you choose different things that only apply to specific matrices. Right now, we don't need to worry about them yet, because we've only talked about general operators for matrices. You go to edit, and you press, let's start with using A, it brings you to a menu. In the menu, you can adjust the dimensions. So let's, for example, if you make it 4 by 2, make something that has 4 rows and 2 columns. If you make it 1 by 9, makes it something that has 1 row and 9 columns. And after you set a appropriate dimension, you just go and plug in for the numbers at the corresponding positions. Now, the reason why this is useful is, let's take this example that we had. Let's take a random matrix. Let's make it 3 by 3 this time. 3, 3, 3, 2, 1, 0, 8, 9, 10. Make this a matrix. And then plug them in. 8, 3, 1, 9, 3, 6, 10. And now let's make another matrix. 2, 1, 0, 2, 2, 3, 3, 8, 9. Oh, press second and then quit, and then go back to the matrix menu. Go back to edit again and choose B this time. Make another 3 by 3 matrix and plug in this one, 2, 2, 3, 1, 2, 0, 0, 3, 9. Quit out. And if you go back, you'll see that on the matrices, you'll see 3 by 3 next to both A and B. You do this, press enter on A, and then it just comes out as a collection of like a variable. So if you were to do A and then type in plus, go back to the matrix menu and do B, it gives you the corresponding matrix after performing the corresponding operator that you just plugged in. This works for other things as well, like multiplication, division, as long as the dimensions of the matrices match up. Now, let's move on to the hmm, let's move on to multiplication. So let's start out something fresh. So we have a matrix, right? Now, different types of matrices have different dimensions. What is important here is that you can't always multiply matrices by other matrices. What you can though is multiply matrices by a set uh constant. So if you were to do 8, 9, 3, 2 times or times 2, just multiply every single corresponding like individual number by 2 internally. 16, 6, 18, 1. I mean 18, 4. Same goes for division. Now, where it gets complicated is when you start having to multiply matrices by matrices. So what you do here is essentially you wanna it's do you know what's the term for it? I think it's called foiling when you like let's say you have like three let's say you have like A plus B times C plus D. Now how you like multiply this to here, this to there, this to here, and this to here? It's kinda something similar. Let's say you have a 2, 3, 4, 8 times 1, 1, 1, 3. Essentially, uh, what you do here is you take one row. What's the best way to explain this? Hmm, oh, wait. Oh, I realized what I needed to explain. Sorry. So actually, before we get to that, let's cover some. The reason why wasn't sure how to explain this with what we had is because I hadn't taught you an important concept yet. So the thing about matrices is that they're simply like a variable, right? Like we saw in the calculator that A gave, if you plugged in for A, what A was showing on the calculator was what we had plugged in. And it was just all condensed into one symbol. Now, because it's effectively like a variable, it's a bit weird. So when you multiply it, most rules hold, but there's one important thing that is not. So matrix A times matrix B does not equal matrix B times matrix A. Now, the reason it's like this is because, uh, depending on how you do it in multiplication between matrices, the row multiplies to the columns. Like, depending on which one the order is very important when you do matrix with operators because whatever comes first and whatever comes last is what defines which row you're multiplying to which column. And In this case, you would be multiplying the column of, yeah, the column of A onto the rows of B. No, the rows, yeah, the horizontal rows of A onto the columns of B. So in this case, it is not the same. All right, so going back, let's write this out. So 3, 2. We have these two here, right? So essentially what you do is, assuming this is A, you multiply 3 by 2, and then it doesn't add end here, is which is what makes it hard. What you do here is that you multiply this 2 here, right? Well, now you add it to 2 times 1. So you multiply this 2 with this, and this to this, and you add it together. And for here, what you do this is multiply for this is just the first like thing. It's just the top right here in A. Multiply 5 5 to 2 and 6 to 1. So 10 plus 6. Then we move on to this row. 3 to 3 and 2 to 2. 5 to 3 and 6 to 2. So because in this case you're multiplying each row to a column, uh, it makes a big difference in where it is and whether you multiply it. Because let's say we switch B and A, right? So we have 2, 3, 1, 2 times 3, 2, 3, 2, 5, 6. Let's just test something with the bottom thing. So this was the second row times the first row, right? You multiply the second row, 1 times 2, 3 plus 10. This is this equals 13, which does not equal 16 that we should have gotten if we multiplied A times B. So this rule doesn't hold. However, some operators that do hold is stuff like assuming you have two matrices, this still holds. Equals AB plus C. AC. The reason this holds is because it's not changing the order of which gets multiplied to which. Like B and C were not getting multiplied initially. B and C were still getting added, and they're still getting added, so it doesn't make a difference. So what this is saying here is that you can this distributive property still works out. That's probably gonna be it for today, and next time we'll get into talking about how we deal with matrices that are different dimensions.